In this fourth video for Chapter 6, we're going to be looking at two final reactions for this chapter. In both of the reactions, we are going to be adding oxygen. In one case, we're going to use what's called a peroxy acid as our oxygen donor, and in the other reaction, we're going to use ozone. For the final video, just looking forward to this one, we're going to be going back and looking at many of the reactions we've learned in this chapter, but we're going to take into account stereochemistry. All right? And the final thing we'll do in this chapter is to learn how to use these reactions in a sequence to convert one molecule into another, or in a process called organic synthesis. All right, so let's look at these reactions with peroxy acid and with ozone. All right, so the first reaction here is going to form what we call an epoxide. Peroxides are actually ethers, but they're an interesting class of ethers, and that they're ethers that are in a three-membered ring. Okay, so we have two groups, one on each end of this ring, and this is just a kind of an ether. Okay, but it's more reactive than most other ethers because we've built in a lot of ring strain into this. Alright, so we're going to learn how to make these ethers now, and we're going to learn what reactions it can do later on. Okay, the way that an epoxide ring is formed is starting with an alkene. Alright, and we're going to react this alkene with something called a peroxycarboxylic acid. Okay, so it has this structure here. And I'm just going to put an R group over here. We can think of this peroxycarboxylic acid, let's write it down here, peroxycarboxylic acid. Sometimes we just refer to it as a peroxy acid. We can think of this peroxy acid as kind of a combination of this molecule. So what's this? This is hydrogen peroxide and a carboxylic acid. Okay. Carboxylic acid. So what we've done is we've kind of taken this kind of peroxide bond and we've added another oxygen into the carboxylic acid to form this peroxycarboxylic acid. We have these two oxygens. Alright, so when we do this reaction, one of the oxygens gets added to the pi bond. And we get this three-membered epoxide ring, and our byproduct is just a carboxylic acid. Okay, so one of the oxygens in the peroxycarboxylic acid is donated or added to the pi bond. Turns out that it's this oxygen right here. Alright, so let's look at how this takes place. This is kind of a cool mechanism, I think. And it kind of relates to the bromination reaction, so the formation of the bromonium ion. Alright, so I'm going to draw this peroxy acid in a certain way. Okay, so I'm going to draw it like this. Like that. And we're going to compare this to our bromination reaction. Okay, in the bromination reaction, remember we drew this dibromide end on, and so what we did is we showed the pi bond reacting with the bromine, and in the epoxidation reaction, the pi bond's going to react with this oxygen. Okay? Then the bromide left, and in this case we're going to draw this arrow over to here. All right? We're going to form a new pi bond, and the non-bonding electrons on the bromine went back down to form the three-membered ring. So in the epoxidation, this center carbon, or the carbon of this peroxy acid, if it forms a pi bond here, it can't hold any more bonds, so it has to give up this pi bond, and what it does is it comes down and reacts with that proton, and the electrons in that oxygen-hydrogen bond go down to form the three-membered ring. So let's see if we can figure out what's happened here. Let's do it in both of these. So over here, for the bromination reaction, we've done this before, right? We formed a bond. Oops, I didn't want to do that. We formed a bond with this arrow between one carbon and the bromine, and then from this non-bonding electrons we formed another bond. And so in this case we got this three-membered ring with bromine, and we got a plus charge on the bromine, so we got the bromonium ion, and then we got bromide as a byproduct. Alright, so if we look at this epoxidation reaction, notice that this bond is being broken. Right? We're forming a bond between the oxygen here. This is broken, like this one is, and these electrons, which are connected to the oxygen, are going to go back down here. So what we get is this epoxide, and over here we formed a pi bond here, ROH, right, and form the carboxylic acid. Alright, so like I mentioned, this is an interesting mechanism. Be able to compare these two mechanisms, and then we'll use these epoxides later on. One thing about both of these reactions is all these arrows that we're showing in this first step all take place simultaneously. So both of these steps that I'm showing here are concerted. Okay, remember, when we have something that's concerted, it means that all bond forming and breaking happens simultaneously. Alright, so this is the epoxidation reaction. The next reaction is going to be the reaction of an alkene with ozone. Okay, so let's think about just the structure of ozone first. So ozone is O3. Alright, so let's draw out a Lewis structure for ozone. Okay, so the first thing, remember, when we want to do a Lewis structure is we have to figure out how many valence electrons that we have to work with. So valence electrons. Alright, we just have 3 oxygens. Each oxygen has 6 electrons. So 3 times 6, we have 18 valence electrons. Okay, so let's try to put those together. Okay, we're going to put these oxygens in a row like this. Alright, so that just used up 4, right? And we can put some on the end, 4, 6, 8, where should we put them? 10, 12, 14, is that right? 2, 4, 6, 8, 10, 12, 14. Where else? 16, 18. All right, does that look good? No, not quite yet. Notice this one has only 6 electrons. All right, so what can we do to give that oxygen 8 electrons as well? All right, so what we can do is we can take one of these pairs of electrons and we're going to move it in here to make a double bond. Okay, so then we're going to have this. We're going to have 2 pairs of electrons here. We've made a pi bond. This goes to the other oxygen. Right? This oxygen still has 1 pair. And we'll just fill the rest of these in like we had before. All right. So now, do all of the atoms, all the oxygens have complete octets? Yep, because this one, remember when we count octets, they're able to count all 4 of these. So we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. They all have octets. All right, so let's calculate some formal charges then. What about this atom right here? So the formal charge, remember, equals the valence of that atom. All right, so that equals 6 for oxygen. I'm going to subtract from this the total number of non-bonding electrons, 4, plus half of the, or no, those, yeah, the non-bonding, half of the bonding. So there's 4 bonding. Divide that by 2. So we got 6 minus 4 plus 2 is 6, 0. Okay, so that oxygen is neutral. And we kind of know this before, that if we have an oxygen with 2 bonds to it and 2 non-bonding pairs, then it should be neutral. So we've seen alcohols, right? Ethers. All right, what about this oxygen? Formal charge equals 6 minus, all right, so we want the total number of non-bonding electrons is only 2 in this one, plus the total number of bonding, 2, 4, 6, divided by 2. And so in the parentheses we have 2 plus 3 is 5, 6 minus 5 equals 1. Okay, so there's going to be a plus charge on that oxygen. And what about this last oxygen then? Okay, so here we have a formal charge. This equals 6 minus, we have 6 non-bonding electrons, 6 plus, we have only 2 bonding, 2 divided by 2. This equals 6 minus 7 equals minus 1. So we got minus here. So ozone, even though it's neutral overall, has a minus and a plus charge. So the next thing I want to consider here is, what about the hybridization of this carbon? Because we're going to think about what geometry this has. Okay, so it has 1 pi bond. That means it should be sp2, right? And so it should be trigonal planar. So let's just draw some of these bonds with lines now. So we're going to have a double bond to one side. We have non-bonding electrons here, 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 and 3 pairs over here. A minus and a plus. We get this kind of bent structure. The other interesting thing about this is then we have a resonance structure. If we use a pair of electrons there to form a new pi bond, these electrons can go back onto this oxygen, and we form a resonance structure that just has the bonds shifted to the other side. So the center oxygen is still plus, but it's the other end of the ozone that has the minus. Okay, so what kind of a reaction takes place here? Okay, so what's going to happen is we're going to have a carbon-carbon double bond. and we're going to add to it ozone. And what we're going to get in general is we're going to get two different molecules. So we're going to cleave that that carbon-carbon double bond, and we're going to form two carbonyl compounds. The actual identity of the carbonyl compounds depends upon how we run the reaction, and we'll talk about that in just a minute. So one way that we can figure out what gets formed is essentially all we're doing is breaking this bond. I'm going to break that. I'm just going to break it like this, right? Just severed that bond in the middle, and then I'm just going to add an oxygen into each side. All right, and then we're going to end up with some other oxygen species, right, for the third oxygen, but that depends on how we run the reaction. Okay? All right, so let's look at how this actually takes place. Okay, so start with our carbon-carbon double bond and our ozone. Minus, plus, like this. Alright, so we can think about this as an electrophilic addition reaction, just like the other reactions we've been seeing. So the first step is going to be the pi bond and the carbon-carbon bond reacting with ozone. So it's going to end up reacting with this end of the oxygen, because what we can then do is push those electrons onto the center oxygen. So the electron's going to move toward that plus. That's going to start building a plus charge here, but what can happen is that this oxygen with its minus charge can donate its electrons down like this. So if we do that, let's see what we get. We now have only a single bond between the two carbons. We formed a bond to this oxygen. This one has a single bond here. This one still has a single bond. Each of these oxygens have two pairs of electrons, non-bonding electrons now. And so everything is neutral. All right. This is a reaction we could call a cycloaddition. We're just adding two molecules together and we're making a cyclic structure. This first intermediate, this is called the mole ozonide. I don't know who thought that up. Alright, so then let's see what happens after that. This one is kind of cool. Alright, so what happens is that this pair of electrons can go down like this to form a pi bond, so form a carbonyl, that's what we're trying to form here, and it's going to break the bond between the carbons. That's going to go over to here to form the other carbonyl, and this bond is going to open up. So we're going to end up with two different molecules here. We have this carbon-carbon there, and we get O, a carbonyl on this side, and on the other side, we're going to have a double bond. Oops, let's do this in red. A double bond to the O, but this has a second O attached. So this one has a plus, and this one has a minus. Okay? So we're still net neutral. Alright, so in the first one we've added ozone, we formed the mole ozonide, and we've split the molecule into two pieces. Alright, but we're not done yet. Alright? What has to happen here is that these two species are going to rejoin. Alright, so I am going to just come down this way, and I'm going to rotate this molecule. Okay, so I'm going to draw the one on the left the same. Okay, and the one on the right, I'm just going to draw it upside down. So here's the carbon here. We have a double bond to an oxygen, and that has a single bond to another oxygen, plus minus here, and these recombine. This is always kind of amazing to me. This can react with the carbon, and this pi bond reacts with this carbon, and these electrons go over here. Okay, let's see what we have now. Alright, we have a carbon, like this. We have a single bond to an oxygen. That oxygen goes over to the other carbon. Right? That goes down, single bond down to an oxygen, another single bond to an oxygen, and that goes to this carbon. So look at that, we reformed it, and now we have no carbon-carbon bond in the middle, and we have an oxygen on one side and two oxygens on the other side. This one is called the ozonide. Okay? Alright, so this is where it gets kind of tricky. And this is this is basically as far as we're going to go as far as the mechanism. So we're going to do something here called the workup. Alright, so this is really a second part of the reaction. And it's going to give us slightly different products depending upon what the workup is. Both of them are we're going to go to here, but then the workup can convert it to something else. Alright, so before I show you the workup, I have to show ships between carbonyl compounds, right? Because we're going to form some carbonyl compounds. So let's look at these alcohols on the left. Alright, so remember we can classify alcohols based upon how many carbons are attached to the carbon bearing the OH. Alright, so we'd call this a primary alcohol. This one has two R groups, two carbons. This would be called a secondary alcohol. Alright, so if we convert that primary alcohol to this functional group over here, this is called an aldehyde. What have we done? Right? What we've done here is we've removed these two hydrogens. And when we remove hydrogens, we call it, in organic chemistry, we call it an oxidation. Right? Remember in Gen Chem we usually talked about removing or adding electrons, but in organic chemistry we talk about either removing H's or adding oxygen. Alright? Okay, so this first step here then, we call this an oxidation. Alright, so then if we go from this aldehyde, what's this last compound called? This is called a carboxylic acid, right? What have we done here? Okay, in this case what we've done is we've added this oxygen right here. Right? So this is another oxidation. Oops. Okay, so if those are oxidations, what would it be if we went the other way? Right? The other way is going to be a reduction, right? Oxidations and reductions are going in the opposite directions. Reduction. Alright, so primary alcohols, aldehydes, and carboxylic acids are all related to one another by oxidation-reduction chemistry. Alright, if we start with a secondary alcohol, however, and we go over here, we remove two hydrogens again, this hydrogen and this hydrogen, we form a pi bond there, we don't get an aldehyde, but we get what's called a ketone. Okay, so this has this part here. This is called the carbonyl. Right? The ketone has two carbons attached to the carbonyl. An aldehyde has a carbon and a hydrogen. All right, so these relationships are the same. This is oxidation. Going back the other way, if we were doing it, would be a reduction. Okay, so reduction and oxidation is removing H's or adding O. A reduction means either adding H's, okay, like that hydrogenation reaction we talked about, or removing O. Okay, so just backwards. Okay, so this is going to be important. Understanding of this is going to be important in how reaction. Okay. All right, so let's draw out the product of the first step. So if we do the ozonolysis of this upper left alkene, we're going to draw the ozonide of this. Okay, so it's going to go to there and to there, and in the middle here we're going to have an oxygen at one side and two oxygens on the other side. All right, so this is the ozonide. All right, so we have three different ways to run this reaction, or three different workups that we can do. The first one that I'm going to show you is to use this one here is dimethyl sulfide. You can also do this with zinc metal. Okay, when we do that, we get just what I was suggesting before. Right, so what we do is we essentially go and we draw this molecule like this. We just cleave this, and we just add an oxygen into each side. These would be H's here. All right, so if we have one carbon and one hydrogen on each end, we get two aldehydes. Okay? This is kind of the baseline for this reaction. This is in the middle. Okay, so if we do our workup, instead of using dimethyl sulfide, we use, right here, we use hydrogen peroxide. Then these aldehydes that are initially formed get oxidized. All right? Remember, what do aldehydes, or what can aldehydes get oxidized to? Okay, they can get oxidized, so this would still be the O, but they can get oxidized to an OH here. So aldehydes get oxidized to carboxylic acids. Oops. Okay, so when we use hydrogen peroxide, this is oxidizing okay, we get the carboxylic acids. All right? Well, we'll do that down below. If we use this species down here at the bottom, okay, this is called sodium borohydride. A sodium borohydride is a reducing agent. Okay, and so the two aldehydes that are formed initially are reduced. Okay, so when we reduce an aldehyde, what do we get? We get a primary alcohol. So we get an alcohol here, and we get an alcohol here. So we get alcohols. Alright, so all of these are possible from the ozonolysis. It just depends upon how we do this workup. If we do dimethyl sulfide, all we have to do is cleave this bond, pull those two carbons apart and add oxygen, right? And that's what we do in this middle line. If we add hydrogen peroxide, we oxidize whatever we have there, and we can get carboxylic acids if the double bond is substituted like that. If we use sodium borohydride, we get it reduced. Alright, so let's look one more example. Okay, so let's do the middle one again first. Well, let's draw out the ozonide. Okay, so we have this. We just take off the double bond. We put all those carbons in, right? We just add an oxygen to one side, two oxygens to the other side. All right, so there's our ozonide. If we use dimethyl sulfide, all we do is break this bond. All right, so there's one side of it with part of that double bond. And here's the other side. And all we do is we add oxygens right there. All right, because there's a hydrogen here, we got a hydrogen here. Right? So notice that the side that had the hydrogen gets an aldehyde. The other side has two carbons, and so this makes a ketone. Okay? If we use our oxidizing workup, hydrogen peroxide, the ketone can't be oxidized any further. Alright, so we just get a ketone, but for the aldehyde side, that can be oxidized further. Right, and so this one forms a carboxylic acid. Alright, the bottom one, if we use the reducing conditions, instead of the ketone, we get a secondary alcohol, and instead of the aldehyde, just like up above, we get a primary alcohol. Okay, so again, if we just break this bond and add oxygens, that's what we get if we use dimethyl sulfide. If we add hydrogen peroxide, we oxidize both of these groups if we can. So an aldehyde can get oxidized to a carboxylic acid. A ketone can't get oxidized further. And the reason is there's no H here. We have to be able to remove an H, right? So it stays the same. If we use the reducing conditions, we can reduce the ketone to the secondary alcohol, and we can reduce the aldehyde to the primary alcohol. Okay? All right, let's look at a couple of examples here. All right, so we're going to do 3 different ozonolyses. All right, it looks like, oh, I thought I made a change to this bottom one. We'll get to that in a minute. Okay, so the first one, we do the ozonolysis. Notice we got to keep the temperature low, and we're using dimethyl sulfide. So all we do, we cleave this, and make these 2 double bonds. Remember, this would have 2 H's here. So we have 2 H's over here and here. And all we do is add an oxygen each side. So on this side, we have a ketone. Over here, this is a special aldehyde. Has 2 H's. This is, you've probably smelled this before, formaldehyde. Right, it's used when you do dissections for preserving animals and things like that. Okay, so the next one uses hydrogen peroxide. So again, we're going to cleave this, and each side is going to be oxidized. So notice that this double bond is in a ring, so we're going to open up the ring in the process. So we're going to get this, and we have a double bond here, and a double bond here. we can put an oxygen here and an oxygen here, right? So the top one is a ketone, the bottom one is an aldehyde, so the aldehyde gets further oxidized. Right, so we get a ketone and a carboxylic acid. Alright, the next one I wanted to have in here, sodium borohydride. Okay, so look at this. What we're trying to do is figure out what molecule, if it's treated with ozone and worked up with sodium borohydride, could give this product, or these two products. Notice there's two here. One of them has 3 alcohols, and then we have another one here, just methanol. So if we want to work backwards, and we see that we have reducing conditions, we have to think about what we would have right before we do the reduction. Right? So we could oxidize these in our in our head to carbonyls. Like this. And this one over here would be formaldehyde. Right? So notice if we look back up to the top, this is where we got formaldehyde up there. So that has to be some double bond that's sticking out. There's only one carbon on the double bond. So we have to figure out how we can break some of these apart. Alright, so let's think how we could combine these. So let's count from here. 1, 2, 3, 4, 5. So if we kind of went backwards and we linked these two together, we'd get a 5-membered ring. So let's try that. Okay, and we'd have a double bond in the ring. Right, so that's what would cleave to get those 2 carbonyls. Sticking off of this, though, we have this aldehyde here, and we still have the formaldehyde. So we'd have to have a carbon-carbon double bond like that. So in this ozonolysis, we'd cleave here, and we'd cleave here. So we'd cleave off the end, we'd get formaldehyde for this end, we'd get an alcohol here, and then we count around here and get another alcohol. So that would be this structure here. Alright, so we have one other possibility. What if this carbon was connected to this carbon over here? Okay, so that goes over to 6. So in this case, we'd have a 6-membered ring. Right? And we'd have to have a double bond in that 6-membered ring, but then within the ring, we'd have this oxygen. And that oxygen would be connected to the formaldehyde. So we'd have this. So in this case, we could cleave this bond, we could cleave this bond, right? We'd still get our formaldehyde from down this bottom one. Then we get an alcohol here, 1, 2, 3, 4, 5, we'd get an alcohol, and 6, we'd get an alcohol. Alright, so either of those would work to give that product under these ozonolysis conditions. Alright, so those are our new reactions. We've added peroxy acids. Remember, if we add peroxy acids, we get epoxides. We add ozone, we do what's called an ozonolysis. Remember that lysis means to cleave. So we're breaking a double bond with ozone, and we get usually some kind of carbonyls, though those carbonyls can be reduced to alcohols. Okay, pretty tricky, huh? Alright, so in the next video, like I mentioned, we're going to look back, we're going to review back through some of our reactions we've already learned, and we're going to look at both the stereochemistry that's involved in those reactions, and we're going to look at how we can combine them into sequences of reactions that could be used with organic synthesis.